All right, chemistry, let's take a look at the first portion of our video lecture for chapter 15. We're talking about acids and bases for the first time. What I want you to be able to do after this particular video, I want you to be able to list 5 general properties of aqueous acids and bases. Again, general properties, and what we'll start with. And then these next 2 bullets are actually more review back from the nomenclature portion of the course in chapter 7. Name common binary acids and oxyacids given their formulas, then list 5 acids commonly used in industry and laboratory, and give 2 properties of each. Then some new stuff, define acid and base according to the Arrhenius theory of ionization. Now, we're going to emphasize the Arrhenius definition here because there's more than one definition for an acid and base. And we're not going to really get into the reasons why each of them has a shortcoming and what each of them really accomplishes. We're just going to go over 3 different theories for acid and base definitions. Arrhenius is going to be the first one. Then lastly, we're going to talk about the strengths of acids and bases. So explain the differences between strong and weak acids and bases. Here we go. Don't forget to press pause if you feel like you need to. It's a good idea to just take a moment, a couple of seconds, in between major ideas or slides to gather your thoughts before you move on. Aqueous solutions of acids have a sour taste. In fact, that's actually where our word acid comes from. Ancient peoples didn't know what an acid was chemically, but they did know that when they put it in their mouth, it had a sour taste. And so they would say, this is sour. And their word for sour is our word acidic. Now, we are going to talk a little bit about acid-base indicators right here. It's an indicator, whether it's either a fluid that you put into solution or it's a piece of paper that you put into solution, and it will change color to match the pH. Right? It'll show you what the pH is of whatever solution you're looking at. It's an indicator. It indicates acid or base. So obviously, an acid will change the color of an acid-base indicator to reflect that it's an acid. Some acids react with active metals and release hydrogen gas. A couple of things to remember here. An active metal, go back to chapter 8 in the activity series. We see that an active metal is one that reacts more readily. Right? It's that list of elements. The more active elements were at the top, the least active elements were at the bottom. So the more active metals, those metals at the top of the series, when they react with certain acids, they will form hydrogen gas as a product. And remember, Brinkelhoff, hydrogen's a diatomic molecule, it is H2. Number 4, acids react with bases to produce salts and water. That's one of the easiest definitions of what acids do with bases. They produce salts and water. Now, the type of salts that they can make can vary wildly, but it's always going to be some sort of salt, an ionic compound, something from the left side of the periodic table, something from the right side of the periodic table, and water. And lastly, acids conduct electric current. Remember when we went over ionic bonding versus covalent bonding back in chapter 6, we talked about the idea that an ionic compound that is solid will not conduct electricity because the ions can't move. They're fixed in place because they're part of a lattice structure. But if we were to dissolve that same ionic compound in water, now they will not be fixed together in a lattice structure. They'll be able to move around freely. And in fact, the ability of an ion to move around freely in solution is the thing that conducts electrical current. And so an acid, as we'll see more a little bit later on, does dissociate in water to generate 2 ions at least. Therefore, they can move around and conduct electrical current. Now, we do need to be able to name these things in this chapter. Remember, a binary acid is an acid that contains only 2 different elements, hydrogen and then one other element. It's usually going to be the more electronegative elements. So remember, the most electronegative element is fluorine, and then we have chlorine, bromine, and iodine. When we go to name them, the name of the binary acid begins with the prefix hydro. So if you see just a single element back here, like fluorine, chlorine, bromine, iodine, with hydrogen, the name of that acid is going to begin with hydro. If you see a polyatomic ion, it's not going to start with hydro because it's not that simple element. So it's going to start with hydro. The root of the name of the second element follows that prefix. So that prefix hydro is followed by the root of the second element's name. So fluorine, fluor. Chlorine, chlor. Bromine, bro. Iodine, iode. Right? So we're going to take those roots and we're going to follow that prefix. So hydrofluor, hydrochlor, hydrobro, hydroiode. And then the name then ends with a suffix. Hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Oop, too fast. Here we have a table that's going to be useful for you. The things that we just listed, the four that we just listed: hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. And then one more. Here's a sulfur. Right? It's just sulfur, so it's hydrosulfuric acid. Hydrosulfuric acid. We don't just have binary acids here. So we have oxyacids. And oxyacid is an acid that is a compound of hydrogen, oxygen, and some third element that's usually a nonmetal. But it's hydrogen, oxygen, some third element. So notice we have hydrogen, oxygen, a third element. In this case, it's nitrogen. Hydrogen, oxygen, a third element. In this case, it's sulfur. The names of the oxyacids follow a pattern, and the names of the anions are based on the names of the acids. And some of the patterns aren't super obvious, but some of them are, so let's look at those. So here's our sulfuric acid. Notice this isn't hydrosulfuric acid because this is not a binary acid. It's an oxyacid, and so we don't see the word hydro in front. We don't see the word hydro in front. We don't see hydro in front of any of these because the anion is always a polyatomic ion. It's not a simple single element. And so we see that this is called acetic acid because the ion is called acetate. This is carbonic acid because the anion is called carbonate. This is called iodic, right? Realize it's not hydroiodic like we saw with the binary compounds, the binary acids. This is an oxyacid, so we don't see the word hydro. That anion is called iodate, right? We have this anion called hypochlorite, so hypochlorous acid. Chlorite, chlorous acid. Chlorate, chloric acid. Perchlorate, perchloric acid. And so we see this pattern that as we increase in number of oxygens, the suffix changes, right? So we have hypochlorite. This is the fewest oxygens, hypo. Then we have chlorite, no hypo, but they still have the ite ending. So hypochlorite to chlorite, we've increased in one oxygen. Then we go from chlorite to chlorate, we've increased one more oxygen. And then perchlorate, now we have the most oxygens, ClO4. In terms of the 5 common acids used in industry and in lab, these are them. You have sulfuric acid, nitric acid, phosphoric acid, hydrochloric acid, and acetic acid. Again, go back to the previous slide, get used to what those anions are called and the connection between the name of the anion and the name of that acid. Now let's talk about bases. You're going to see a couple things here that seem really, really similar because they are very, very similar. One, aqueous solutions of bases taste bitter. Again, why is everyone tasting stuff? Because acids and bases began to be described far before the chemical basis for what was going on was knowable. It was possible to know it. And so one of the simple ways that you would describe something is by its taste. It's not the best system to use, but for ancient peoples, it was some of the best that they had. Now, it tastes bitter. Vegetables taste bitter. They have a bitter flavor. Most of them have some sort of bitter flavor because vegetables are mostly alkaline in nature. All right, they have a basic nature on the inside. Whereas fruits typically tend to be either sweet or sour. That's because they're mostly acidic. Right? They might not be very strong acids. Sometimes they are a little bit more aggressive, like citric acid for citrus fruits. But that has to do with the nature of the solution inside that plant. Now, obviously, a base will change the color of an acid-base indicator as well because it's an acid-base indicator. It's indicating acid or base, so it's going to indicate base by changing it into a particular color. A dilute aqueous solution of base will feel slippery, kind of like soap on your hand. Bases, again, these would be the exact same 4 and 5 as we had on the acid screen. Bases react with acids to produce salts and water. Well, that's the exact same thing that we read last time. We just had acids listed first and bases listed second. There's still acids and bases reacting with one another, and when they do, they produce a salt and a water. And because bases will also dissociate in water to generate ions, they conduct an electrical current. A little too far. Next, we want to introduce the Arrhenius definition of an acid and base. So this is the Arrhenius definition. We'll have other ones next video, but this one's the Arrhenius. An Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions, which is H+1, in aqueous solution. Now, hydrogen ion, H+. Now, what I'd like to get down before we go any further, depending on who you are and what type of data you have access to, you're either going to measure the concentration of free hydrogen ions, which is that H+, or the concentration of the hydronium ion, which is H3O+. It's water with an extra hydrogen. And concentration of hydrogen ions and concentration of hydronium ions are both used to distinguish an acid, especially in the Arrhenius definition. So don't freak out if you see the hydrogen ion pointed out or the hydronium ion pointed out, because they end up being the same thing. Where is this hydrogen going to go? It's going to hook onto a water to make the H3O+. So if we're talking about this hydrogen ion or the H3O+, we're still talking about the result of an Arrhenius acid. An Arrhenius base is a substance that increases the concentration of hydroxide ions. And if you remember from our nomenclature days, or at least you have your polyatomic ion sheet out, the hydroxide ion is OH-. Right, so an Arrhenius base, when you put it in the solution, it is going to generate hydroxide ions.
According to Arrhenius's definition, acids are substances that increase the concentration of hydrogen ions in aqueous solution. The hydrogen ions join with water to form hydronium ions. Acids that fit the Arrhenius definition are all molecular compounds with ionizable hydrogen atoms. According to Arrhenius's definition, bases are substances that increase the concentration of hydroxide ions. Bases that meet the Arrhenius definition are all molecular compounds with ionizable hydroxide groups.
So an Arrhenius acid, Arrhenius acids are molecular compounds with ionizable hydrogens. What does that mean? It means that a hydrogen can pop off, right? Remember, an Arrhenius acid is something that when you put it into solution, it's going to increase the concentration of the hydrogen ion concentration. Why? Because a hydrogen can pop off, right? It's ionizing. It's being thrown off the molecule. So let's look at nitric acid. It's an acid, so it's going to increase either, remember, it depends on how you look at it, either hydrogen ion concentration or the hydronium ion concentration. Here's our nitric acid. See this little hydrogen up here? Okay, this is hydrogen. Here's water, right? Oxygen, hydrogen, H2O. After this nitric acid loses or ionizes this hydrogen, right? Notice that it's just the nitrate ion over here. There's no hydrogen. So this is just the bare ion. It's not an acid anymore. It's done what the acid's going to do. It lost that hydrogen. Where did that hydrogen go? It attached to this water, making it positive overall. It's H3O+, and we call it the hydronium ion. So again, it's okay to talk about the concentration of hydrogen ion or the concentration of hydronium ion. They're synonymous in this topic. And again, all aqueous acids are electrolytes, because remember what an electrolyte is something that when it's put into solution conducts an electrical current. Anything, acid or base or whatever, it's going to, if it's an electrolyte, it will conduct an electrical current. What is an electrical current? It's propagated by the movement of charged species. Well, guess what? Charged species, charged species. Here you go. A lot of charged species that can move around. That's going to conduct an electrical current. Therefore, electrolyte. We're going to get into the strengths of acids and bases here. And it might seem like it's a lot of work at first, but I'd like to encourage you. The nice thing if you move on to AP chemistry, the way that you memorize weak acids versus strong acids is you memorize 6 strong acids. Every other acid is weak. That's it. That's how you do it. These 6 are strong. You memorize this list. Everything else is weak no matter what. But notice how no matter how strong the acid is, it's always reducing an increased hydronium ion concentration. So a strong acid is one that ionizes completely in aqueous solution. When I put it into water, when it becomes aqueous in nature, it completely ionizes. Not in the sense that an individual molecule will definitely lose its hydrogen ion. Every single molecule loses its hydrogen ion, right? Every single one of these, every single one of these, every single one of these jettisons that proton to generate ions in solution. If every single one of them loses a hydrogen ion, it's considered a strong acid. Here's some examples of strong acids. Again, it's a pretty short list that you have to memorize. Everything else is considered weak. And a weak acid is an acid that releases few hydrogen ions in aqueous solution. Right? So things like hydronium, any sort of acid that's already been dissolved, especially the organic molecules, okay, like the acid that's derived from cyanide, this CN. This is an acid because this hydrogen can ionize. It just doesn't always do that. So out of a particular batch of HCN, only about 10% of these molecules are going to ionize as hydrogen. So not all of the hydrogens get ionized. Only few hydrogens get ionized. Therefore, it is a weak acid. Strengths of bases. Most bases are ionic compounds, at least according to the Arrhenius definition. An Arrhenius base is going to mostly be an ionic compound containing a metal cation and a hydroxide anion. Remember, hydroxide is OH minus. When we dissolve it in water, it looks like this. So here's our metal and hydroxide, sodium hydroxide, sodium's the metal. Sodium hydroxide, we dissolve it in water, here's the water, and it dissociates into two ions. One thing I want to point out here, this weird G with a hat is actually supposed to be a minus sign to show the -1 charge. I just can't change that because this actually, the whole thing is an image. I can't actually get in there and edit it. So just hang with me there, that's a minus sign. Ammonia is molecular, it's not ionic, but it still produces hydroxide ions when it reacts with water, right? So here's the ammonia, here's the water. What's happening? One of the hydrogens from the water is being torn off and added to the ammonia to create the ammonium ion right here. Oh, guess what? Here's our old friend OH minus. Remember, this is a minus. And that's what defines an Arrhenius base, the production of OH minus. Again, similar idea, not a lot to memorize, right? There's a specific set of things that you want to memorize. Everything else is going to be considered the weak bases, so there's not actually as much to memorize as you think. But notice, in each of these bases reacting, there's a production of OH, hydroxide. That's the Arrhenius definition of an acid.
For acids and bases, strength and weakness refer to the amount of ionization that takes place in solution. Nitric acid is a strong acid because it ionizes almost completely in water. Acetic acid is a weak acid because it only partially ionizes in water. This incomplete ionization is represented by a set of arrows pointing in both directions. The system contains both ions and molecules in equilibrium. In the reverse reaction, some of the acetate ions that form recombine with the hydronium ions to form acetic acid. The same holds true for bases. Weak bases only partially ionize, whereas strong bases ionize completely.
Last slide, the relationship between concentration of hydronium to concentration of hydroxide. Remember, this can also be written as the concentration of H+, right? It's interchangeable. So, if we look at our balance here and we have way more hydronium than we have hydroxide, we consider that thing acidic right here. See, when there's more hydronium, that's what we call acidic. When there's more hydroxide than hydronium, we call it basic. But when they're in balance, we call it a neutral solution.